All right, in the derivatives that we've looked at before, we have not found derivatives of a composite function. And the chain rule deals with composite functions. For instance, we can find the derivative of y equals x squared plus 1. But right now, we don't know how to find the derivative of the square root of x squared plus 1. This is a composite function. The second function is a composite function. We could find the derivative of y equals the sine of x, but we don't know how to find the derivative of y equals the sine of 6x. This again represents a composite function. Put my x here. We could find the derivative quite easily of 3x plus 2, but we don't have the tools at this point to find the derivative of 3x plus 2 squared unless we multiply it out and take the derivative. And then again, we could find this one, x plus the tangent of x, but the chain rule would be required to find x plus the tangent of x squared. Now notice, only the x is squared. It's not the tangent of x squared, but we would need the chain rule for that as well. So let's just look for a few minutes on how we might decompose a function before we talk about how to use the chain rule. All right, if we let y equal to f of g of x, a composite function, we're going to take a function and we are going to identify the inner function and then rewrite it in terms of u. So for instance, if I have y equals 1 over x plus 1, then u in this case is going to be x plus 1. And we can rewrite y as y equals 1 over u. I just sort of decomposed and then put that function back together again. I think you'll see why when we look at the definition of the chain rule. So if I have y equals the sine of 2x, what might u be? 2x. And so we could rewrite y as y equals the sine of u. And that should have been an x and not a u. All right, if I had y equals the square root of 3x squared minus x plus 1, what is u in this case? 3x squared minus x plus 1. So we could rewrite it as y equals square root of u. Okay, so I think you get the idea there of how we're redefining u. So that will help us when we talk about the definition of the chain rule. All right, so if, I'm just going to give you the definition and then we'll look at some examples of the chain rule. If y is equal to f of u, and that is a differentiable function of u, and I will abbreviate. This is a differentiable function of u. And u is equal to g of x. And that is a differentiable function of x. Differentiable function of x. I know it gets kind of wordy, but I want to be sure we understand what's going on. Then y equals f of g of x is a differentiable function of x. And if we take the derivative of y with respect to x, that is going to be equal to the derivative of y with respect to u times the derivative of u with respect to x. That's one way that it's written, and that's why I wanted us to look at how we back out and find out what u is. I wanted you to see this because you could see this form somewhere, but my preferred derivative, or the preferred way that I think makes it easier to understand for us, is that if we look at it as the derivative of y with respect to x of f of g of x. That is our composite function. This is going to be equal to the derivative of the outer function times the derivative of the inner function. The derivative of the outer function times the derivative of the inner function. This probably would make a little bit more sense than the other definition. Okay, because we're used to seeing things as f of g of x. So let's look at a couple of examples. Okay, what's the inner function here? X squared plus 1 is our inner function. Our outer function would be x cubed. All right, so if we want to take this derivative, we take the derivative of the outer function, which is going to be 3, and we keep this here. Of course, we have to subtract 1 from the 3. Now we multiply it by the derivative of the inner function, and you could just rewrite that as 6x times x squared plus 1 squared. And there is your derivative. Now, obviously, you could cube x squared plus 1 and take the derivative. A little bit of trouble, but I mean, it's doable. Especially if that were squared, you could easily multiply it out and then take the derivative. But that's not always an easy option. If we wanted to take the derivative of x squared plus 1 to the 50th, I don't think I'd want to try to multiply that out. So we would definitely want to use a chain rule. You could find the derivative of this function without the chain rule, but I don't think you could find the derivative of x squared plus 1 to the 50th without the chain rule. So if we take the derivative here, it's just going to be 50 times x squared plus 1 to the 49th times 2x. And here we'll go ahead and simplify it, 100x times x squared plus 1 to the 49th. And we have got our derivative. All right, the special case of the chain rule just involves a function raised to a power. The derivative of u to the n is simply n times u to the n minus 1 times u prime. That's considered a special case of the chain rule, and you'll see that a lot. In fact, that's what we just did. We just used this special case of the chain rule. If we had f of x equals 3x minus 2x squared cubed, and we want to take the derivative. I don't think I would want to take the time to multiply that out. It just would take a while to do all that. So we can use that, what we've been doing, 3 times the inner function, 3x minus 2x squared times 3 minus 4x. You could leave it like this, or you could distribute your 3 into this factor, but you are welcome to leave it just like that. All right, let's look at One like this. Okay, negative 7 over 2t minus 3 squared. Notice down here, it's going to be a case where we're going to need the chain rule. So, do you want to use a quotient rule? Or can it be rewritten so you don't have to use a quotient rule?
It can be rewritten.
How would you rewrite it?
Move it up to the top and just do like minus 2 for the exponent.
Okay. Anytime that if you just have a constant in the numerator, you want to rewrite it with a negative exponent to take the derivative. Be much easier than trying to use the quotient rule. So here when we take the derivative now, we can use that special case, and we would have 14 times 2t minus 3 to the negative 3 times 2. And you never leave negative exponents in your final answer, so it's 28 over 2t minus 3 cubed. Okay, this is involving the product rule and the chain rule. Because we obviously have two factors multiplied together, and for the square root of 1 minus x squared, we'll have to use the chain rule. So I'm going to first rewrite this as x squared times 1 minus x squared to the 1/2. So if we take this derivative, it's the first term times the derivative of the second term, which in this case is going to be 1/2 times 1 minus x squared to the negative 1/2 times negative 2x. The thing you have to watch out for with the product rule is we just did a lot, but we're not finished. Because now we have to take the second term and multiply it by the derivative of the first term. If I look at this, notice that I have 1/2 times negative 2, so those 2's cancel, and we still have a negative x. All right, so I'm going to factor out what's common to both. We have an x that's common to both. I can just take it here. So I'm going to factor out an x, and I have this term that's common to both. The 1 minus x squared to the negative 1/2 is what's common to both of them. I'm really just factoring that out or dividing that out. We always take the lowest exponent. Now, when I do that, I still have an x times a negative x. So we're still going to have a negative x squared. Now, let's think about this. 1 minus x squared to the 1/2 divided by 1 minus x squared to the negative 1/2. What happens when I do that? What do I get? What's 1/2 minus a negative 1/2?
0. No. 1.
It is 1. So we're going to be left with, did I take that in the wrong spot? Oh, wait, negative 1/2 minus a negative 1/2. That's what it is. I wrote that down wrong. This would be for the second one. What?
That should be
Negative
negative.
1/2 minus a negative 1/2 is
Negative. No, 0.
0. And anything to the 0 power is 1. So right here, we're just going to have a 1. Hopefully I didn't totally confuse you. This was x squared to the negative 1/2, not a positive 1/2. Just factored it out of that first term. Negative 1/2 minus a negative 1/2 is 0. So this term went to 1. Okay? Plus, I factored out this x. I'm left with 2. Now what's 1/2 minus a negative 1/2? 1. So 1 minus x squared to the first power. Right, so if we simplify here, I'm going to have negative x squared minus, plus 2 minus 2x squared. So we'll have 2 minus 3x squared when we simplify what's inside. We can move this to the denominator. And this stays in the numerator. So here is our derivative for this function that we started with. All right, here we'll have to use the quotient rule and the chain rule. And there, you could rewrite this with the negative exponent, but there's no real benefit to doing that. But we do know that this is the same as x over x squared plus 1 to the 1/3. Pardon?
The original one is 4.
Oh, thank you. All right, so when we take the derivative, we're going to have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is 1/3 x squared plus 4, and 1/3 minus 3/3 is negative 2/3, times the derivative of, that should be a 3, x squared plus 4, all over the denominator squared. We simplify the numerator a little bit before we factor out. Minus, we will have 2/3 x squared times x squared plus 4 to the negative 2/3.
Wait, where did you get that x squared after the 2/3?
The x in front and this x. This is all over x squared plus 4 to the 2/3. Neatness helps a lot here. All right, so what's common to both terms on the top? X squared plus 4, and we always factor out the lowest exponent. So I'm going to factor out x squared plus 4 to the negative 2/3. And we're left with, now, 1/3 minus a negative 2/3 gives me 1, right? 1/3, we're dividing out the negative 2/3. So 1/3 minus a negative 2/3 gives me 1. So we have x squared plus 4 minus 2/3 x squared. And x, here I've got, if I divide this by itself, we just get 1. And this is all over x squared plus 4 to the 2/3. Notice these match. So I can move that to the bottom.
So it equals
X squared plus 4 to the 2/3, and we're going to have 3/3 x squared minus 2/3 x squared. Would it be proper to leave that fraction there? How would we get rid of that fraction in the numerator? We don't ever want to leave a fraction in the numerator. What could we do? Oscar?
just
What rule?
what's that name?
It's not a calculus rule.
I don't get use
So to get rid of the fraction in the numerator, I'm going to multiply the top and the bottom by 3, which gives me x squared plus 12 over 3 times x squared plus 4 to the 2/3. Yes, that denominator should have been 4/3. When I added the 2/3, I was thinking it, but I just didn't write it down. Thank you.